So in this problem, we're going to look at two questions from Pinter's chapter 10, section B. And I want to start by saying there are a ton of problems in this chapter. And I think even a good bunch in chapter 11 too. We can go take a quick little look. Oh yeah, a whole lot of questions in chapters 10 and 11. And so I've tried to pick out like a reasonable collection of problems to look at, some of which for these videos, some of which for homework, but also when I'm going to like prepare an exam, one of the best places to look for good questions are just other questions in the textbook. And so in my head, there are a whole goldmine of problems here that are worth it to consider for the exam. I'm telling you this so that if you're planning on doing well on the exam, maybe in addition to the problems that we see here, you go check out a few more of those problems, especially from those sections for which, well, we don't really get to them because we're only going to make so many problem videos. So to get started, in this video, we're going to look at B2 and also B6. So B2 asks, sorry about that. I don't think you guys saw that, but I touched something and it messed up the recording for a sec. So B2 asks, what is the order of the element 6 in Z mod 16Z? And in essence, that's asking us, how many multiples of 6 do I need before I get to 16? So let's just write them down. 6, 12, and the next would be 18. 18 is 2 in Z mod 16. And so now we're going to go around again, but everything is increased by 2. So we have 8 and 14. And now I add 6. I get to 20, which is 4. And now everything is the same as here, but increased by 4. So we have 10. And then lastly is 16, which is 0. So how many elements do we need? 1, 2, 3, 4, 5, 6, 7, 8. So the order of 6, maybe we could write this if we want to write this. A little bit of a silly thing to write, but I think you guys will know what we mean. The order of 6, not the absolute value of 6, is equal to 8. I think that's a funny looking equation, so I'm going to leave it. I think it looks good. Nice little clickbait for our videos today. All right, good. B6 asks, can an element of an infinite group have finite order? The answer is yes. The reason for the confusion is an infinite cyclic group can only have cyclic subgroups. And since the elements of those subgroups are powers of the generator of the infinite cyclic group, they also cannot have finite order. So they would also have to be infinite. But all we need is an infinite non-cyclic group for this to be the case. So I'm going to show you guys an even weirder example, just because it seems like it's a good thing for you to know about. It's an infinite group where every element has finite order. So not only some elements have finite order, every element has finite order. So here's the group. The group is constructed by infinite tuples where all but finitely many AI are 0, and all AI belong to the same Z mod NZ. Actually, you don't even need this, that they all belong to the same Z mod NZ, but that makes it easy to understand. So because this is all but finally many of these guys are 0, you can't ever have like any kind of increasing chain that's also controlled by them all being in the same Z mod NZ. If this was allowed to vary, then this argument wouldn't work. These are kind of like guardrails to prevent us from going off into some weird territory. But in this case, every element is at most order n. In fact, I don't even think I need all but finitely many either. Just because no matter what, every AI, right? If I took that element and I call it G, right? Then since these are Z mod NZs, we could use additive notation. N times G would be NA1, NA2, and so on, right? For all of these. But since these guys are all in Z mod NZ each, these are all equal to 0, right? And therefore, this is equal to E, the neutral element of this crazy group. And so this is a huge infinite group because there are infinitely many terms, and they're all allowed to be Z mod NZ, but every element has order n. So there are much easier examples you can find. So I'll let you guys look for simple examples. But I like this example because I think that if you can push a property to the extreme, it's probably good to do that, right? To keep that in the back of your mind as like something really weird might be happening. And then you might use this on other problems.